Hello again. In this lesson, we're going to solve a couple of problems related with Galileo's relativity. The first problem says, an observer in a reference frame S observes the motion of an object and describes its motion as r vector equal to t squared minus 2t I hat plus 8t squared j hat minus k hat. Another observer in a reference frame S prime describes the motion of the same object as r hat prime equal to t squared plus 3t I hat plus 8t squared j hat minus k hat. A. Determine the speed constant of the S prime reference frame with respect to the S reference frame. B. Verify that the acceleration is the same as seen from both reference frames. So these two are the equations of motion of that particle as observed from one reference frame, the reference frame S, and this is as observed from the reference frame S prime. And from Galileo transformation equations, we know that r is equals to r prime plus the velocity relative times t. So the position as measured from one reference frame is the same as the position measured from the other reference frame plus the relative velocity between both reference frames times t. So we can consider that we have the following reference frame. This is reference frame S, and then we have reference frame S prime that are observing the motion of this particle, and they want to observe and describe the motion of the same particle. So, because you're just using this Galileo equation of transformation, we will write r here as t squared minus 2t I hat plus 8t squared j hat minus k is equals to r prime plus the relative velocity plus, I will write it down here, plus, and that will have three components, vxt I hat plus vyt j hat plus vzt zt k hat. Now I will decompose this equation of three dimensions into three equations of one dimension. First, for the I hat direction, I will have this t squared minus 2t is equals to this other term here, t squared plus 3t plus this other term in the I hat direction plus vxt. For the j hat direction, I have 8t squared equals to this term of j, 8t squared plus this other term of j plus vyt, and then the k hat is going to be -1 is equals to -1 plus vzt. So these are the three equations that I have, and now I want to solve them to find what is vx, vy, vz. So from the first equation, I have that this t squared cancels this other t squared, and I have -2t minus 3t is equals to vxt. From here, if I solve for vx, I find that vx has to be -5 meters per second. Everything was in the SI units. That's the component, the x component of the velocity. From the second equation, 8t squared cancels 8t squares, and this result gives me the velocity in the y direction is 0. This other equation, -1 cancels this -1, and here I have that the last Vz is equals to 0 meters per second. So the final result, the relative velocity, is going to be -5 I hat, that's the x-axis, meters per second. So this is the relative velocity between both reference frames. So that's the velocity of S prime as seen from the reference frame S. Now, if we want to find the acceleration, what I will have to do is just derive the position to get the velocity, derive it again to get the acceleration. I will do that for S and S prime, and I will check if both accelerations are the same. That is B, the derivative dr with respect to t is going to be, this is 2t minus 2. Derivative of a constant is 0. That is the acceleration. This was the velocity. Now let's go for the prime. Now I derive this other term, this other expression here. And just by comparing them, we can see that yes, A of t is equals to A prime of t. Quod erat demonstrandum. The second problem says that a swimmer wants to swim upstream 500 meters and then swim back if the speed of the water of the river is 1 meter per second and that of the swimmer is 1.3 meters per second. Determine how long does the swimmer needs to go back and forth. Then what is the speed of the swimmer as seen from someone on the riverbank? In this problem too, we have a river here and the water of the river is going downstream, so it's going down, and we'll call this v sub r, the velocity of the river, and then I will call u the velocity of the swimmer, which is first is going upstream and then is going to go downstream. We have an observer here on the bank of the river. The water of the river will be one reference frame, we can call it S. This is an observer at the reference frame S prime, and the velocity that this observer on the bank of the river is observing is going to be u sub prime 1. I will put 1 when the swimmer is going upstream and 2 when it's going downstream. So the velocity in that prime reference frame is going to be the velocity of the swimmer in its reference frame minus the relative velocity, because the velocity of the water is going down while the swimmer first is going up. So this is going to be upstream. Now when it's going downstream, u prime, the prime makes reference to the reference frame, the 2 makes reference that it's going downstream. This is going to be u plus the relative velocity, the velocity of the river. This is downstream. Now, part A of this problem. The motion we know that is described after Galileo's equation as x is equals to x naught plus u prime t. So that's the position of the swimmer, the initial position of the swimmer, the velocity as observed by this observer, and the time elapsed. So the distance traveled going upstream, we have that x minus x of 0 is equals to 500 meters, and that's equal to u1 prime t1. Because I'm looking for the time that needs to go upstream, I will solve for t1 here. t1 is 500 over u1 prime, and this u1 prime, I grab it from here, I substitute. This is 500 over u minus vr. This is 500 over 1.3 minus 1.0, and that you substitute, and it gives you 1667 seconds. So that's the time that the swimmer needs to go upstream. Now let's do the same for downstream. This is the down, and this is going to be, this t2 is going to be 500 with the same distance over u prime 2. So this is 500 over u prime 2 is up here, is u plus v sub r. This is 500 over 1.3 plus 1.0, and this you substitute in the calculator and you get 217 seconds. That's the time that the swimmer needs to go downstream, the same distance of 500 meters. What's the total time? Time t is t1 plus t2. That's going to be 1667 plus 217. That gives us 1884 seconds. Something like about half an hour, something like that. Okay, that's for A. Let's do B now. We want to know what's the velocity of the swimmer as seen from the river bank when it's going upstream and downstream. Well, again, Galileo transformations, or just using these expressions here, we get that u1 prime is u minus vr. So u in this case was that 1.3 minus 0.3, that is, minus 1.0, and that is 0.3 meters per second. U prime 2 is going to be u plus v sub r. Now when it's going downstream, the river is helping. This is 1.3 plus 1.0, and that is 2.3 meters per second. Well, that's all for this lesson. And remember, physical distancing, yes. Distancing from physics, never.